eternal dance of our solar system, one planet has captivated our imagination like no other. Mars, a world of rust-red hues, has tantalized us with its secrets and possibilities. For centuries, scientists have been drawn to its mystique, and plenty of stories have been written exploring its potential as a home to advanced civilizations, possibly encounters with alien life forms, and as an alternative home for the resettlement of the human species. But the red planet's hostile environment, a toxic brew of thin air, freezing temperatures, and scarce water, has kept our dreams of settling on Mars in the realm of science fiction until now. With the development of advanced robotics and artificial intelligence, coupled with breakthroughs in sustainable energy technologies, the prospect of actually terraforming Mars, transforming its harsh, barren landscape into a habitable environment suitable for human life, is starting to feel like a real possibility. Join us on an epic adventure, from initial robotic missions to the establishment of sustainable habitats, as we refine what it means to explore, adapt, and push the limits of what is possible in our quest to expand beyond Earth. Phase 1. Exploration and Initial Preparations, 2030 to 2035. Robotic missions spearhead the terraforming of Mars, deploying state-of-the-art probes equipped with advanced spectrometers and drill systems. These probes meticulously analyze Martian soil composition, atmospheric gases, and subsurface water ice. Automated rovers hardened against Martian radiation traverse rugged terrain, collecting geological samples and transmitting real-time data streams back to Earth-based command centers. High-resolution cameras capture panoramic views, aiding in terrain mapping crucial for future colonization efforts. Simultaneously, a fleet of orbital satellites and sensor-laden platforms encircle Mars, forming a comprehensive surveillance network. Advanced spectrometers and infrared scanners monitor atmospheric dynamics, pinpointing greenhouse gas concentrations and identifying potential water reservoirs beneath the Martian surface. Continuous telemetry streams provide vital insights into seasonal climate patterns, seismic activity, and solar radiation levels. This orbital vanguard ensures a constant flow of actionable data, laying the foundation for strategic decision-making in subsequent terraforming phases. 2035 to 2040. Building upon robotic mission successes, human outpost construction on Mars commences with advanced habitat modules crafted from reinforced regolith and carbon nanotube composites. These materials provide structural integrity while shielding against solar radiation and temperature extremes. Prefabricated inflatable habitats deployed by autonomous drones are swiftly assembled and interconnected to form a robust, pressurized living environment. Interior hydroponic farms utilize Martian regolith and recycled water to sustainably grow nutrient-rich crops, ensuring food self-sufficiency for the outpost's inhabitants. The inaugural human crew, comprising multidisciplinary scientists and engineers, commences groundbreaking research initiatives within the outpost research laboratories. They leverage on-site resource utilization technologies to extract water ice from nearby subsurface deposits, essential for life support and future fuel production. Advanced 3D printers fabricate spare parts and experimental equipment, optimizing operational autonomy and reducing reliance on Earth-based resupply missions. Continuous environmental monitoring systems track atmospheric composition changes and geological dynamics, providing invaluable insights for ongoing terraforming strategy development. Hey guys, before we get into the next phase, we did a video on why it is so difficult to get to Mars. Be sure to check it out. Phase 2. Warming the atmosphere, 2040. An announcement is made. Scientists are given the permission to initiate the atmospheric transformation by deploying autonomous drilling platforms and subterranean extraction units across Martian regolith and polar ice caps. These units employ high-efficiency CO2 extraction technologies, utilizing cryogenic processes to liberate trapped carbon dioxide. Advanced robotic systems systematically release the extracted CO2 into the atmosphere, while emission control protocols ensure minimal environmental disruption. This controlled release amplifies the greenhouse effect, raising atmospheric pressure and surface temperatures incrementally, and facilitating the melting of polar ice. Alongside these developments, an array of high-precision orbital mirrors and laser-equipped satellites are deployed to focus sunlight onto the Martian polar ice caps. These mirrors, positioned at strategic Lagrange points, harness concentrated solar energy to rapidly increase ice temperatures. This concentrated solar heat accelerates the sublimation of CO2 and the release of water vapor, enhancing the greenhouse gas density in the atmosphere. Cutting-edge thermal imaging and real-time data analysis systems monitor the ice cap's melting rates, ensuring optimal energy application and progress towards atmospheric thickening. Nuclear Enhanced Warming Strategy 2050. To achieve rapid atmospheric transformation, scientists implement a bold and cutting-edge strategy. This strategy involves the deployment of precision nuclear payloads from Earth to Mars. Earth-based command centers orchestrate the launch and trajectory of the nuclear payloads, ensuring precise targeting of Martian sites rich in frozen carbon dioxide and water reserves. Autonomous guidance systems navigate the hostile Martian atmosphere, guiding payloads to designated impact zones with pinpoint accuracy. Upon reaching their targets, nuclear warheads initiate controlled detonations, triggering massive releases of greenhouse gases into the Martian atmosphere. Real-time telemetry and remote monitoring technologies provide continuous feedback, optimizing detonation strategies and ensuring maximal atmospheric impact. 2051. Advanced satellite arrays and orbital surveillance platforms continuously monitor atmospheric dynamics and radiation levels post-detonation. AI-driven algorithms and predictive modeling assess the immediate and long-term impacts of nuclear-enhanced warming strategies, mitigating potential environmental risks. Comprehensive containment protocols and emergency response measures stand ready to address any unforeseen consequences, safeguarding ongoing terraforming efforts and ensuring the sustainable advancement of the atmospheric transformation of Mars. 2060. The lack of a strong magnetic field on Mars leaves its atmosphere vulnerable to solar wind, which gradually strips away atmospheric particles. To protect and sustain the newly thickened atmosphere, scientists embark on creating an artificial magnetic shield to deflect harmful solar wind particles. This shield comprises a network of superconducting magnets strategically positioned at Lagrange points of Mars. Advanced computational simulations and 3D modeling techniques optimize the placement and design of these magnets, ensuring maximum coverage and efficacy. The superconducting materials chosen for their durability and efficiency are engineered to generate a robust protective magnetic field. Autonomous robotic assembly platforms and precision deployment systems facilitate their installation. At the Lagrange points of Mars, their combined magnetic fields effectively detect solar wind particles. Integrated telemetry and feedback mechanisms continuously monitor magnet performance, ensuring real-time operational efficiency and adaptation to space weather conditions. With the shield effectively protecting the atmosphere of Mars from solar wind erosion, atmospheric pressure and temperature regimes essential for sustaining ongoing terraforming efforts can now be maintained. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell, you'll help us to make products of even higher quality. Now, let's jump into the next phase. Phase 3. Enhancing atmospheric composition. 2060. Bioengineered bacteria designed to break down Martian rocks are introduced into the planet. These bacteria secrete organic acids and enzymes that gradually decompose rocky substrates, releasing essential minerals and creating a more hospitable soil matrix. This process not only generates fertile soil but also helps anchor nitrogen in the Martian regolith, facilitating the growth of subsequent plant life. With a stabilized Martian atmosphere enriched with CO2, scientists now focus on nitrogen enrichment. Robotic drones release genetically engineered nitrogen-fixing bacteria into the Martian air and soil. These bacteria convert atmospheric nitrogen into nitrates, making it available for plant uptake. 2065. Controlled cultivation chambers and open field experiments introduced nitrogen-fixing plants, legumes such as clover and alfalfa, specifically engineered to thrive in Martian conditions, further enhanced the nitrogen cycle by creating a symbiotic relationship with the introduced bacteria. Advanced hydroponic systems and automated irrigation techniques support plant growth, maximizing nitrogen fixation and atmospheric enrichment. Advanced sensor networks and AI-driven analytical tools continuously monitor changes in atmospheric nitrogen levels and soil chemistry, while predictive models simulate long-term ecological impacts, ensuring sustainable and balanced nitrogen levels within the evolving Martian biosphere. 2070. With the introduction of genetically engineered cyanobacteria and algae, efforts to oxygenate the Martian atmosphere intensified. These organisms are specifically designed to perform photosynthesis under Martian conditions, utilizing CO2 and producing oxygen as a byproduct. Autonomous drones disperse these microorganisms across Martian soil and into newly formed bodies of water, initiating large-scale oxygen production. 2073. Controlled environments, including biodomes and subterranean biospheres, are established to support the growth of oxygen-producing organisms. Sophisticated monitoring systems track oxygen levels and the health of photosynthetic organisms. AI algorithms analyze data to optimize growth conditions and predict oxygen output. As initial experiments prove successful, efforts scale up, expanding the range of oxygen-producing habitats across Mars. Gradually, the increased oxygen levels contribute to a more breathable atmosphere, laying the groundwork for the eventual introduction of more complex plant and animal life. Phase 4. Building habitats and ecosystems. 2080. Building on the success of nitrogen fixation and oxygen production, the next 2 decades concentrate on expanding Martian ecosystems. Diverse plant species, from pioneer species like mosses and lichens to more complex plants such as drought-resistant ferns, ryegrasses, and hardy shrubs like the Arctic willow, pave the way for forests, grasslands, and wetlands in controlled environments. Advanced irrigation and nutrient delivery systems support these developments as efforts intensify to establish permanent habitats capable of supporting human life. Surface habitats and underground shelters expand and reinforce using local resources such as Martian soil and minerals. Advanced construction techniques create sustainable living spaces resilient to Martian conditions, ensuring a safe environment for growing populations. 2090. Scientists introduce terrestrial organisms and extremophiles to establish self-sustaining ecosystems on Mars. Extremophiles like tardigrades and lichen can stabilize local environments and foster biological diversity over time. Other organisms such as Deinococcus radiodurans, celebrated for their resistance to radiation, bolster genetic diversity and resilience within Martian habitats. Scientists study firsthand how these species interact and adapt in simulated Martian conditions, using enclosed biospheres and controlled environments as testing grounds. These controlled environments mimic natural cycles of light, temperature, and moisture, nurturing the growth of pioneering species and supporting ecological succession. Continuous monitoring of Martian ecological systems using AI-driven analytics and remote sensing technologies ensures stability and sustainable development. Adaptive management strategies based on ecological feedback optimize habitat conditions and species introductions, safeguarding against disruptions and supporting the evolution of Martian colonies into self-sustaining ecosystems for future human habitation. 2100. Efforts intensify to prepare Mars for large-scale human settlements, following the establishment of habitats and ecosystems. Infrastructure development focuses on creating self-sufficient Martian cities equipped with advanced energy generation systems, efficient waste management facilities, and robust transportation networks. Innovative technologies such as solar farms and fusion reactors provide sustainable energy sources essential for Martian colonies' autonomy. 2124. International collaboration drives sustainable urban planning initiatives on Mars, guided by ethical frameworks and regulatory standards. Integrated city designs prioritize resource efficiency and environmental stewardship, minimizing ecological footprint. Advanced recycling systems and closed-loop water management ensure efficient use of resources, supporting the long-term sustainability and resilience of Martian settlements. Phase 5. Long-term stabilization and maintenance. 2150. Advanced sensor networks and AI-driven climate models continuously monitor the atmosphere of Mars, temperature, and pressure. Nanotechnology-enhanced sensors provide real-time data, enabling precise adjustments to maintain habitable conditions for human settlement. Climate control technologies, including atmospheric processors and weather modification tools like ionization towers, create artificial rainfall and regulate local weather patterns, mitigating extreme climate events. 2200. Integrated terraforming infrastructure powered by orbital reflectors and nanotech materials stabilizes Martian environments. Automated systems manage atmospheric gases and solar radiation, ensuring long-term habitat sustainability. International collaboration promotes sustainable development practices and ethical governance frameworks. Shared research facilities and regulatory standards prioritize environmental stewardship, supporting responsible resource management and fostering economic cooperation among Martian colonies. Phase 6. Achieving self-sufficiency and independence. 2300. Interdependent colonies emerge across Mars, advancing economic diversity and cooperation among settlements. Martian colonies transition towards achieving self-sufficiency in vital resources like food, water, and construction materials. Robust industrial sectors are developed to manufacture these essentials locally, decreasing reliance on Earth and enhancing resilience. Advanced hydroponic farms and genetic engineering facilitate efficient food production. Automated construction methods using Martian materials support infrastructure expansion as the blooming Martian planetary civilization takes shape. Martian colonies leverage their unique geological resources and technological expertise to contribute to the Martian economy. For example, colonies in mineral-rich regions extract rare metals essential for advanced technologies, while agricultural settlements utilize advanced hydroponic and genetic engineering techniques to produce diverse food crops. Innovative water extraction technologies harness Martian ice and regolith to sustainably secure vital water resources for Martian colonies using advanced robotic drills equipped with thermal and chemical extraction methods, while solar-powered distillation units and graphene filters purify extracted water. Hyperloop systems crisscross the Martian surface, transporting goods and passengers at unprecedented speeds. Spaceports serve as hubs for interplanetary trade, launching cargo ships laden with Martian goods and raw materials back to Earth and other celestial bodies. Virtual reality and holographic communication platforms enhance cultural exchange among settlers, promoting collaboration in scientific endeavors. Continuous innovation in robotics, AI, and biotechnology drives sustainable autonomy, guided by ethical frameworks for responsible resource management and environmental preservation. 2400. Sustainable growth strategies prioritize environmental stewardship and resource management, creating circular economic principles that drive waste reduction and recycling efforts, and optimizing resource use across Martian colonies. 2500. As Mars achieves self-sufficiency, governance structures evolve to meet the needs of its growing population. Martian colonies establish representative assemblies and regulatory bodies, crafting policies tailored to local challenges and opportunities. Diplomatic relations between Mars and Earth mature, encouraging collaboration on scientific research, trade agreements, and cultural exchanges. Joint initiatives address common challenges such as climate change and resource management, strengthening interplanetary cooperation. Communication satellites and AI-driven diplomacy platforms facilitate dialogue and negotiation. A unique Martian culture emerges, blending terrestrial heritage with the distinct experiences of Martian colonization and terraforming. Cultural expressions from art and literature to music and cuisine reflect the resilience and creativity of Martian settlers. Virtual reality simulations and immersive experiences preserve Earth traditions while celebrating Martian achievements, birthing a sense of shared identity across colonies. What new technologies do you think will be most important for Mars colonization? How do you see life and communities developing on Mars in the future? We look forward to hearing your thoughts and ideas in the comments below. If you like this video, then you should check out the one on your screen. This is why it would be preferable to colonize Titan instead of Mars. Thanks for watching.